Hello guys, welcome to a new lecture of data mining, a video lecture. This is gonna be the last topic of the course we're gonna talk about. Then next week we will have a last, summarizing lecture, not even, like we're just gonna explore how to see an end-to-end project from beginning to the end. And then probably next Thursday there will be some, Q&A session with some live streaming. And I'm gonna think about how to do it. But for the moment, let's focus on today's lecture. Today we have a lot of stuff to talk about, so please let me just go straight to the lecture. And let me say first of all that in order to understand well this lecture, you should remember well our lecture on decision trees. In particular, you need to know how they are, how their algorithm works, what are their strengths and their weaknesses, what are their hyperparameters, what tuning and changing the value of their hyperparameters entails on the predictions of the trees, how they calculate feature importance, and so on. So you need to review all these topics before actually watching this lecture. So if you have forgotten any of these ones, please refer to this lecture, pause this video, take the notebook on that lecture and review it. While if you remember it, there's no problem, just continue watching. Okay, so today's lecture is gonna be about ensembles and ensemble learning. I already uploaded the notebook on Canvas, so you can find it zipped as usual. So you can decide if you want, you can watch the video while I scroll down the notebook, or you can also decide to open the notebook and scroll it by yourself while I'm talking on the background. This is really up to you. Okay, so ensembles. So if you remember when we talked about decision trees, I mentioned something like that decision trees are great tools. For example, if we want to interpret results, are great tools for interpretation, but are not so great usually in accuracy of the predictions. Okay, are not great predictors. Of course, not in all cases, but in general. I also mentioned the fact that decision trees are great, base learners for ensembles. And today we're gonna explore this concept in detail. We're gonna see well what I meant by that, and we're gonna talk more in general about different ways to do ensembles. And let me start by showing you the topics of the day. We will start with an introduction of ensembles, why we might need it. Then we're gonna see two different ensemble methods, bagging and boosting, which have opposite complementary goals, let's say. And for bagging, we're gonna see the bagging method more in general, and then a specific bagging methodology called random forest. For boosting, we will explore the gradient boosting methods and ADA boost. Okay, of course, we will also see how to tune their hyperparameters and so on. In the next block, in the next part, after talking about bagging and boosting, we will see how to try to interpret these algorithms, like the results of these algorithms, with the feature importance chart. Then I will give another few remarks on these methods, and then we will delve into the Python's code. We will see example for all of the methods we're going to explore in this lecture. Last, we will see other ensembles. I will just mention them, but of course it's good for you to know that they are there, and you can feel free to use it whenever you need, also for the final assignment if you want. Then we have Among other methods, we have voting, stacking, and XGBoost that we're gonna see very quickly. And then last, we're gonna also show an example of ensembles, how they perform two ensemble classifiers on the hard dataset as usual. Okay, let me start with a small introduction about why we might need ensembles. So now, just for a moment, let's forget about data mining, and let's think about a situation in life, any type of situation in which we need to take some critical decision, okay, about any type of context in life. So when we need to take a critical decision, we usually will prefer to rely on the opinion on more people, okay, on more experts possibly on the field, rather than only on our own intuition or on the opinion of just one person, okay? And then, so if we could have opinions from several experts, okay, then if we were in a democratic setting, we could use the majority vote to take our final decision, or we could rely on consensus reached among these experts. Okay, now the idea behind ensembles is exactly the same. We have to make a prediction, which is the equivalent of the critical decision we would have in a more general context. But predictions returned by individual estimators, classifiers, or regressors. These type of predictions are individually not that great, okay? And the idea of ensembles is, why don't we use the opinion, so the predictions of not just one but several of these classifiers in order to obtain the final prediction, okay? In order to try to improve the predictions of each of my individual classifiers. And if we can manage to do it, then we will have final predictions that are indeed improved. And when we say improved, if you remember from one of the previous lectures on model selection, we mean improved either in terms of bias or in terms of variance. Because when the problem with individual predictions, when they lead to bad predictions on test data, is that they have either high variance or high bias. And so the idea of ensembles is try to use a lot of high bias estimators to reduce bias, or a lot of high variance estimators to reduce variance. And this is exactly the goal of boosting and bagging. Bagging as the goal of reducing variance, and boosting as the goal of reducing bias. And now we're gonna start by considering bagging as our first ensemble technique. So let's start by considering the bias variance decomposition. If you remember, the expected test error of a prediction from a classifier that we have trained on some training data set is given by the sum of three components, which is called the bias variance decomposition. And these three components are the bias of of the estimator, the variance of the predictions provided by these estimators across several hypothetical samples of the population of interest, and then the noise, which is the irreducible error, which is the error intrinsic in the data, which we cannot improve. Okay, there is no model that can improve this error. Now let's focus on the variance term. You see, it's basically the expected value of the squared discrepancies error between the predictions of my classifier and the expected value of classifiers or a regressor, and the expected value of the of such predictions across the samples of a population, okay, across all possible training and possible all predictors and target values, okay. So ideally, to reduce the variance, so to reduce this term for a predictor that has a low bias and so high variance, to reduce the variance, ideally we would like to obtain a value of the predictions that are as close as possible to the expected value of our classifier across all possible samples. So in this case, what we want to try to achieve, if we want to reduce the variance, is to achieve this in the limit, okay? To try to get my prediction as close as possible as the expected value of the predictions of my estimator. If we manage to achieve this, then we could end up with an estimator that is already low bias, but it is also low variance, okay? Which sounds crazy somehow, but this is exactly what bagging helps us to achieve, and we're gonna see how. Before we continue, it's also important to be aware of a probability rule called the law of large numbers, which I remember you told me in one class that you already had a probability course. So you should remember what the law of large numbers states. But if you don't remember, I left you a link here in the notebook, and I also summarize it in the notebook itself. This law simply states that if we are performing an experiment, and if we perform this experiment enough times, okay, a large enough number of times, where this number of times here is denoted with capital B, then the average of the results of these experiments across across any replication will get closer and closer to the theoretical expected value. Okay, it will approach the expected value of this outcome of the experiment as we increase this number of replications. Okay, and I can show you an example on this. And in order to do that, I'm gonna you can see the example in the notebook, but I want to show you something a bit more interactive. So let's suppose we have 4 coins, okay, and these are all unbiased coins, right? So we have theoretically the same probability of 50% of getting heads and tails. All right, so let's focus on heads, the probability of heads. We have a theoretical probability of heads equal to 50%. Now let's say that each of these 4 coins, we're gonna throw them 10 times, okay? And for each time we record the number, and so the proportion of heads and the proportion of tails, and also the estimated, probability of observing each outcome. So I repeated this simulation, this experiment with Python, and these are the results for our 4 coins after 10 tosses. So for the first coin, we see that we nicely obtain 10 times head and 10 times tail, so that our probability of heads is indeed 50%. For coin 2, however, we observe only 3 heads, so that the probability of heads becomes 30%. For coin 3, the proportion of heads is 0.6, and for coin 4 is 0.4. So what can we say about this experiment? We can say that on average, okay, if we take the average of all these 4 experiments, the average proportion of heads is about 50%, okay, it stays around 50%. However, these proportions show some sort of variability, okay, with each other, like among each other. And so they are not all exactly 0.5, but someone tends to be a bit larger, someone tends to be a bit smaller, and so on. Now I want to show you this experiment has been replicated once again. Maybe the results here are slightly different, but the idea is the same. But this time, instead of a histogram, I report the results on a plot, okay, where I plot on the x-axis the sequence of tosses, the number of tosses of the coins we have, and on the y-axis I report the calculated proportion, okay, after each toss. And so, for example, we see here after the first toss of the coin, each line represents one coin. We have obtained, for example, tail with the green coin, and allegedly we have obtained head with all other coins. Okay. Now, if we continue the experiment, you see that toss after toss, okay, trial after trial, the proportions tend to vary with each other, among each other, and after 10 tosses, as we can see here, we see the usual variability. Okay, in this case, none of the proportion is exactly 0.5. But and as you can see, some of them is 0.6, some of them is 0.4, and so on. Exactly, more or less what we have observed in the previous experiment. Now, the question is, what happens if I increase the number of my trials? So instead of 10 tosses, let's try 50 tosses, okay? And what you can observe is that before we were here, more or less, and there was a specific variability in P, in the estimate of the proportion. However, as you increase this number of trials, what you see, it seems like the variability somehow decreases, and that the proportion of heads starts, to be a bit more stable around 0.5. Now let's try to increase further. Let's go to 500. Yeah, 500. Now it's very clear, if you compare the left side of the plot with the right side of the plot, it's very clear that the variance of such estimates is much more stable, so it's much lower than what it was in the beginning. Now just let me go crazy and let me try 10,000 experiments. And now, after 10,000 experiments, actually even earlier, probably already after 2,000 or 3,000 experiments, we have that the variance of our estimates is basically 0. So that we don't have, it's not exactly 0, but it's much lower than the variance that we had in the beginning of the experiment. And so that we have estimates of P that are very stable around 0. And this is exactly what we mean by decreasing the variance of an estimator. So if you imagine to be in a case where your data set is one of your coins, and the predictions of an estimator are the proportion of heads. Okay, so usually what you are in a situation in which you only have one coin and you make one trial. What we would like to do ideally is to try to replicate our data set so many times, such a way that the predictions of my estimators for each observation, of course, becomes more and more stable. Okay. So that we can basically almost have 0 variance, not exactly 0, but it's much reduced. and also at the same time having low bias, because we will be using estimators with high variance and low bias basically. Now, you can find this experiment in the notebook, of course. Now, what are we just trying to do with bagging is exactly this, is try to replicate our data set so many times that we eventually end up with a very low variance set of predictions. So bagging in practice works like this. First of all, bagging stands for bootstrap aggregating. And bootstrap, I don't know if all of you know it, is a statistical technique that allows us performing estimates of some quantity of interest by also considering the variability and the distribution of these estimates across several samples, which are simply a replicate of the original sample, which is replicated with some resampling technique. And in particular, the resampling technique used in Bootstrap is simply is the following. You have your original sample, and you uniformly draw at random some observations from your sample with replacement, okay? And so the idea is you want to recreate, for example, one new sample with the same sample size of your original dataset, but not with exactly the same units. I mean, some of the units will be the same as in the original dataset, but some of the units will be replicated, and some units in the original dataset simply won't be there, because if you keep the sample size fixed and you sample with replacement, then there is a high chance that some of the units won't be drawn, won't be selected for the new replication. And the idea is not just to do it for one replicate, but for a large number of replicates. Here denoted once again with capital B. So, for example, let's suppose I obtain 1,000 new replications of my dataset, of my original dataset, which is my training data in case of data mining. Now, what Bootstrap does in statistics is for each replicate, you calculate the estimate of interest, for example, a sample mean, a regression coefficient, and so on. Okay, and then, of course, once you obtain 1,000 of these values, you can plot their histogram so that you can observe the distribution across samples of my quantity of interest. And then what is done in practice is, in the end, these results from that are taken from the various replicates are pulled together, are combined, for example, by average, to obtain the final estimate of my quantity of interest. And this is it. This is simply what Bootstrap does. Now I'm gonna show you an example of how to perform a small Bootstrap with a small dataset. Let's suppose we have a small dataset with 3 units, here called A, B, and C, highlighted with the mouse. Now I wanna do Bootstrap with these 3 units. Let's say I wanna make 2 replicates. So I have to keep in mind that I have to use the same sample size as the original dataset, so in this case 3, and so we will have 2 new units. One is unit, one is replicate, Bootstrap replication number 1, and in this case we have drawn at random unit B twice and unit A. In the second replicate we have drawn at random unit A twice and unit C. And so you can imagine that if you're going to estimate 2 times a regression coefficients with these 2 datasets, we won't obtain quite the same estimate, but we would obtain maybe slightly, maybe more different estimates, and these would will help us to take into account and to consider the variability of such estimates across all these samples that we have obtained. Now, why this works? Well, it works first of all because units are, basically, the samples are identically distributed, as all units in the original dataset are supposed to come from the same distribution. And also they are independent because we perform this uniform drawing with replacement. And every time we make the draws, we make it independently. We don't make the draws dependent on what we have drawn, for example, in previous Bootstrap replications. So it can also be shown mathematically, but we don't. I mean, you don't need to do that for this course. Is that the probability for a unit to end up in a new sample, okay, when it's resampled, is about 60%, which means that a unit has about 40% not to end up in a specific new sample. Okay, and for example, if we come back to the example here we saw an example with just 3 units, and you can imagine that if instead of just 3 units we had 100 or 1000 units, then the probability of obtaining different samples at each replicate increases, dramatically. So this is the idea behind Bootstrap. Now, bagging, which I repeat stands for Bootstrap aggregating, it uses the idea of boosting, but instead of applying it to an estimate, okay, we are interested in the prediction, so it applies it to the predictions of a dataset. And here we can see a small representation on how bagging works. So basically the idea is the following. Exactly as we have seen for the Bootstrap, we start from our original dataset. We use Bootstrap, you see, to replicate the dataset by sampling with replacement, as we have just seen. And we, of course, we need to specify how many times we want to perform the replacement. It can be arbitrarily large. We're gonna see a bit more about this in a bit. I mean, we're gonna just talk a bit about how to set B in a bit. And then for each replicated dataset, we we train our estimator of interest. It can be a regressor or a classifier, which provides predictions. And then each prediction will be a poor prediction on its own, because the estimator used at this step is, I repeat, a high variance and low bias estimator, which means it won't be great on a new test set. But then the next step is taking all these individual predictions and combine them in such a way to obtain the final prediction for bagging. Okay. And in general, if indeed the estimator we have used is a high variance one, then bagging greatly benefit from the averaging or from the combination of these estimates. Each of these Bootstrap samples in bagging is also called bag, which means that every time we perform a replication, each unit ends up in a bag. Okay, and yeah, this is the concept. Now, how do we combine the predictions? Where I just mentioned one way, it's by averaging, and in particular this is done in regression. So when this our y hat, our prediction is numerical, is continuous, then what we do is for each prediction we consider, for each unit that we want to predict, we consider its predictions across all of the bootstrap replications, and then we take the average of such predictions, and this is our final bagging estimate. Now, this is for regression. In classification, we have two ways to perform prediction. One is to consider the class, okay, output, that's the output of each estimator for each bagging replication, and then we simply use the majority vote, which means the class that appears the most across all these replications is the one that's gonna be predicted by bagging. Alternatively, an alternative to majority vote is what is called soft voting, which means this y hat in this case, they are the probability for each class, okay? The probability for a unit to be predicted in each specific class. Then we take the average for each class of such probabilities across the bootstrap replications, and we end up with a probability distribution, which is the average of each class across all the bags. And in the end, we simply use the class with the highest final predicted probability, okay, that's been averaged. And this is the final prediction in case of classification. So we have these two alternatives in classification, and scikit-learn by default should be using the soft voting one, this technique. All right, so typical base learners used in bagging. Here I use the term base learner to refer to the to these individual, estimators that we use at each replicate, that are poor on its own, but once bagged they become good. So typical base learners used in bagging are decision trees, and in general ensembles use a lot of decision trees because decision trees have a lot of benefit, produce a lot of benefits for ensemble methods. Among these, we can find that they are able to capture interactions. In case of bagging, we want to have high variance trees, which means we want to have trees that are grown until maximum depth, possibly, so until all leaves are pure. And in that case, trees are really able to capture complex interactions in the data. They have low bias also in this case, in case of fully grown trees, or anyway trees with very large maximum depth. And also trees produce noisy predictions, which can benefit a lot by the averaging performed by bagging. So bagging is great, in theory. It's a great method, but it has a small problem, because it's based on the law of large numbers that we have just explored, and the law of large numbers assumes that our experiments, so the results of our experiments that we're going to average, are independent with each other. However, bagging produces predictions that are not independent, that are actually not independent with each other, but they are just identically distributed. So identical distribution is also an assumption of the law of large numbers, and it actually occurs in bagging because, of course, we are using bootstrap datasets that come from the same original data. Okay, so it makes sense to assume identical distributions. What it doesn't happen is the independence assumption. I'm going to show you why. Now let's suppose we have here these bag trees. Okay. Now Ideally, we would like to have completely independent trees from replication to replication, but if you think well about it, this is hardly possible because trees will tend to be quite similar to each other from replication to replication. For example, it is reasonable to expect that the first split of each tree, okay, so the feature and at the root node of the tree will be almost always the same for all the bagging replications, okay, and maybe the splitting value will vary a bit, but the structure of the tree might be quite similar, starting from the root node, as we said, but then also subsequent split might be easily similar with the others. So what we end up indeed actually in bagging are predictions that are, yes, identically distributed, but they tend to be very correlated with each other. Now, once again, you should recall from your probability courses that the sum, because then with bagging eventually we're going to make a sum of correlated quantities is the variance of correlated quantities is larger than the variance of independent quantities. If you don't remember this, I also left you the link in the notebook. There is the Wikipedia link that shows this rule. And so this means that the gain in variance that we potentially might have with bagging is not that great, or it's less than what it could be because of these correlations, okay, between the predictions, okay, which in turn means that bagging might not always benefit. We might not always have beneficial effects from bagging. But fortunately, there have been ways, researchers have developed ways to overcome these problems. And the most famous one is by far random forests. So now let's gonna talk about random forest. And random forest is simply packing, okay, where the base learners are always trees, usually grown until full depth, with full depth, so until all leaves are pure. And everything is the same as we have seen for bagging, but the main there is only one difference which changed the whole the whole game, and the difference is that if you remember how we build decision trees, you remember that the algorithm of decision trees says that at each iteration we need to decide where to split the tree, okay, what feature and value put at each node. All right. So instead, when deciding on a new split, instead of using all the features in my dataset, what random forest does is using only a subset of these features. And how is this subset selected? Simply, it's randomly selected. So to clarify this, we tell random forest before we run it that it should select when it decides to perform a new split with each tree in the forest, in the bootstrap replications. Each time a tree needs to perform a new split, we tell random forest, okay, random forest, select instead of using all the features, select at random m of them, okay. Here I call this number of features as m, so it becomes a hyperparameter of the model. Select m features and use only this subset of features randomly selected to decide which one is the best for the next split, okay. and random forest does this. It selects the split, and then of course we create 2 new branches, and for the next split it repeats the same procedure. It randomly selects a new set of m features, and it will it will create the new split based on this subset of the features. And so on and so forth for all the nodes in the tree and for all the trees in the forest. Okay, so for each bootstrap replication. And this is it. And this is a simple to understand but also very effective way to decorrelate the trees in each bag. So to reduce the correlation between the predictions, and therefore to make them more likely to be independent, or at least a bit more independent than if we were to use the normal bagging. Okay. Alternatively, you can see bagging as a random forest where m, the number of features selected at each split, is equal to p, is equal to the number of features, the original number of features in my dataset. This, of course, has a double benefit because besides decorrelating the tree, if m, of course, is not too large, it can also speed up the computation so that each tree, although it's grown until full depth, each tree only needs to consider a subset of the features at each iteration. Okay. Here you can find the algorithm. Maybe I can go through it once again just to make sure that you have understood it. So you draw the usual bootstrap, replicates, the bags for the forest. And then for each of these replications, you estimate a tree. Okay, here denoted with capital T and indexed by the specific bootstrap replication. And the tree is grown in this way, starting from the root node. Okay, you select at random m of the features in the dataset. You, among these m features, select the one that leads to the best, improvement, so to the largest improvement in the purity of the node, along with its splitting point. And then we simply split the node. Okay, and then this is repeated in turn for all the nodes that we create in the tree until the tree is fully grown. And then, of course, this is repeated in turn for all the bootstrap replications. And then in the end, the final output is our forest, which is the sum of all trees. Okay, and this is it. This is random forest. So it's basically a way to increase the probability of having more different trees, and so more independent trees, from bootstrap replication to bootstrap replication. Here you can see in the notebook an example with 7 trees. So we have a forest with 7 trees, and of course each tree seems to be very high variance. The data is a 2-feature dataset. We are in a classification case with 2 classes, and the classes, you see, they are very non-linear. They are 2 half moons. You can see that, let's start from tree number 1. You can see that each tree, the decision boundaries estimated by each tree seem to exhibit a very high variance, and somehow seem to overfit the dataset. Okay, and this is done. This happens, as you can see, for all 7 trees, right? However, once we take the average of such trees and we calculate the final forest, we obtain the final forest. we can see not only that the tree doesn't exhibit these large variance anymore, but we see that the decision boundaries are also much more sensible than the boundaries found by each individual tree. And so we can say that in this case, random forest as so the averaging made by random forest has led to a great improvement in variance for each from each individual prediction. And of course, you can imagine that the larger the number of trees in the forest, the greater the benefit in the gain, in the loss of variance that we could achieve. Now, as far as the hyperparameters are concerned, ensembles are nice because we don't have too many hyperparameters to tune, and most of them, they are more or less already set in an automatic way, while others are very easy to set. For example, the number of replications of our bootstrap replications, it can be set as large as we can in general, not always, but in general there shouldn't be a theoretical limit to such number, because the effect of increasing the number of replication is the one that we decrease the variance, while keeping the bias always low, because we are always using low bias estimators at each replication. So the bias is always low, and the effect is that we will see as we increase the number of replications, we see that the variance of the estimators of the predictions decreases. Of course, you have to keep into account the computational power and limitations of your machine when you do this. And another thing that you might notice, that at some point after you increase dramatically the number of iterations, at some point you will see that the gain in variance won't be that significant anymore, or it will just stabilize to some value. In which case you can just stop the bagging or random forest at this point. Now, in random forest we also have the number of features to use at each split of the tree, and this is done can be tuned too, but there are some default values that have been shown to work well in practice, and these are the square root of our number of features rounded to the largest integer in classification, yes, and m equal to p over 3 in regression cases. Okay, so you can use these as default values, and maybe you can play around with these hyperparameters starting from these defaults. And then, of course, you have other hyperparameters that are specific of the base learners. So, for example, if you in random forest decision trees, in bagging can be decision trees as well, but also other estimators. In case of decision trees, the most important parameter is the maximum depth, and usually what is recommended is to grow trees until all leaves are pure, until the possible possible maximum depth. In general, you should always set the base learners in such a way that they have high variance and low bias. Otherwise, doing bagging doesn't make sense, because we wouldn't find a gain, in the quality of the predictions if we already use low variance estimators. Here we see an example where we have a data set classification case with 200 features and 199 observations. We run a random forest, and we are evaluating the misclassification rate, so the lower the better. And what we see is a plot that represents the number of trees, okay, against the misclassification rate for different values of m in random forest, of the number of features to use at each split. And we have m equal to the number of features, in which case we recover the bagging algorithm. M equal to p divided by 2, and m equal to the square root of p as the default value suggested in classification, as we have just seen. And indeed we see that as far as the test error, so the solid lines is concerned, especially when m is equal to square root of p, we see that in the beginning we have quite a large error, but then increasing the number of trees in the forest decreases this test error quite significantly, until it stabilizes more or less about maybe 20% at some point. So you see it decreases, and then with some variability it stabilizes around about 20%. While the training error for all the possible for all the selected number of features m, the training error decreases quite quickly after a few bootstrap replications, and then it goes to 0 immediately. Okay, and after that it never of course it never increases anymore. But what's amazing to see, consider the case with m equal to square root of p, is that we see that the test error decreases, and despite the fact that the training error is at 0, it never increases again, which means the bias is already minimized, and we are also minimizing the variance at the same time, which could seem sort of magic until few lectures ago to you, I guess, but now it has become real. Okay, and so this is the nice aspect of bagging a random forest. They are quite effective in practice, especially random forests have been proven to be very effective and well-working estimators. Now, a last thing I want to tell you about bagging before switching to boosting is the concept of out-of-bag performance. So out-of-bag performance is a feature that's uniquely naturally embedded in bagging, and it has the nice characteristics, nice feature that allows us to evaluate the performance of our bagging algorithm or random forest algorithm without using a validation set. But so we don't need to create a separate validation set when using bagging, but we can use an estimator called out-of-bag error, for example, or out-of-bag performance. And the reason why we can do this is the following. If you remember, we said we have for each unit there is about 60% chance to be included in the bag, so in each bootstrap sample, and 40% chance not to be. Okay, which means that at each bootstrap replication we will quite have some units in the bag and other units out of the bag. So what we can simply do is for each unit we consider all the bootstrap replication in which is not in the bag, okay, and we calculate the average prediction. Okay, it can be in regression, it can be the average probability in classification provided by bagging or random forest for that unit. Okay, averaged of course across all the sample in which the unit is out of the bag. Okay, and so you can see that this is a way, an alternative way to obtain a validation set. Now, once we have this, we can repeat the operation for each unit. Okay, and so we obtain the predictions of our estimator, bagging estimator for each unit. Once we have all these predictions, we can simply consider this average prediction obtained when the unit was out of bag, and compare it with some metric measure, for instance, mixed classification rate, or F1 score, or mean square error in regression, and so on. We compare it with the true target, okay, the true observed target of that unit. And this is what is done here. Okay, now by doing this for all units in our training set, basically, and then we take the average across all units, then we obtain our final estimates of the out-of-bag performance. And this is a simple, also simple to understand, but very effective way to measure the performance of our bagging estimator. Okay, now, so this is it. This is what I wanted to say about out-of-bag. So it's basically an alternative way to obtain a validation set, which is, naturally part of bagging. As we have these out-of-bag samples, we can simply use them to measure model performance. And here I report a plot in which, once again, I plot in the x-axis the number of trees, and this time we have the accuracy measured in the y-axis, so the higher the better in this case. And as you can see, I also used a separate validation set to evaluate my random forest, in this case, after estimating the reported number of trees. And I also report the out-of-bag accuracy. And what you can see is, of course, the two curves are not exactly equal because of sampling difference. But what you can see is that the message they convey are more or less similar. So they convey very similar information. And so this is to prove you that out-of-bag accuracy or out-of-bag performance can be a valid replacement of a validation set performance. Okay, so this was it for bagging. We're gonna switch to boosting. If you feel like having a break, now it's a good time. Take 10 minutes break, 15. Go to your balcony if you have one. Take some fresh air. And then come back. We are gonna talk about boosting. See you in a bit.